So the last related concept to Lewis structures and the VSEPR theory is bond angles. So we've looked at bond angles already when we've looked at just the electron domain geometries. That for two domains, it's 180 degrees. That's as far apart as they can get from one another. Then 120 for 3 and 109.5 for 4. So those are the nice symmetric maximum distances apart for the bonding pairs of electrons. Okay, the issue when you bring in lone pairs is that non-bonding electron pairs repel more than bonding electron pairs. And the idea is that when you have a bonding pair that is between two nuclei, it's going to, so I'm going to skip to the next page, a bonding pair of electrons, sort of thinking of it as this region of where the electrons may exist, it's getting pulled in two directions. It's getting pulled this nuclei, it's getting pulled that nuclei, towards that nuclei. So it's kind of a little bit, if you think about one atom at a time, the electrons are being pulled away from that atom a little bit by the other nuclei. So this nuclei is pulling them this way, and this nuclei is pulling them that way, and that's keeping the electrons sort of spread in between them. But if you have a lone pair of electrons, they're only being pulled this way, and there's nothing pulling it away on this side. So they sort of have more of a presence. They act like a more concentrated charge, and they act more repulsive towards other groups that are around them because of that. So the non-bonding pairs repel one another the most because they are the most repulsive things. Non-bonding pairs repel bonding pairs more than bonding pairs repel one another. So just think of non-bonding pairs as repelling more than bonding pairs. That's the key idea. Okay. And so when we bring that into the concept of bond angle, when you have something like this that's a Lewis structure and all of them are bonding pairs, well, then they repel evenly and all the angles are 120. But if you have a lone pair, like in the SO2 example we've looked at, the lone pair has more repulsion on these bonding pairs, these sticks here. These are the bonding pairs of electrons. So this lone pair pushes them down more than they push back on one another. And so the result is that they're going to get pushed a little bit closer together than the symmetric 120 degrees that we saw in the BF3 example. And so the resulting bond angle, we would say, is about 117 degrees. Now, the exact bond angle is super hard to actually predict, and it has to be measured for all different molecules to know for sure what it will be. But as a general guideline, you can assume that for every non-bonding electron pair, the bond angle will get shrunken down and repelled closer together by about 3 degrees per non-bonding pair of electrons. Okay. So these are the 3 bond angles to try to remember: 180, 120, and 109.5 for the 2, 3, and 4 electron domains. If there's no lone pairs, then those are just the bond angles for the bonds around the central atoms. But if there is one or more lone pair, then just shrink the angles down by about 3 degrees, and you should always be in the correct IB accepted range. So when we're linear, we know the angle is 180. Trigonal planar is 120, and so if you are bent with 3 electron domains, then saying something like 117 will always get you within the accepted range on the IB exam. Tetrahedral is 109.5, so shrinking down approximately by 3 degrees. Usually I would write 107, although you're welcome to write 106 or 106.5. And then if you shrink another 3 degrees, something like 104 or 105, so, or even 103.5. Anything like that should be within the accepted range. So tetrahedral is 109.5. Trigonal pyramidal is the shape where there are 3 bonding pairs and 1 lone pair. That lone pair repels more and shrinks it down to about 107. And the bent, when you have 4 electron domains, those 2 lone pairs shrink the angle down twice. So from 109.5, think of it shrinking down 3 degrees and then another 3 degrees. So approximately down to 104 degrees. Occasionally you get asked to explain bond angles. Sort of step-by-step process to do this on the mark scheme would be first to establish the number of electron domains, and therefore the electron domain geometry and the normal electron domain geometry bond angle. So for the example of SO2, you would first want to say, well, SO2 has 3 electron domains, and so normally we would predict a 120-degree bond angle for something that has 3 electron domains, and it would be trigonal planar. But because it has one non-bonding pair of electrons on the central atom, and because that non-bonding electron repels more than the bonding electron pairs, the remaining bonds get repelled together more closely, and so the angle is about 3 degrees smaller. And therefore, we would predict the angle at about 117. So it has to take a couple of steps to explain a bond angle, establishing what would be normal for that number of domains, stating that non-bonding electron pairs repel more than bonding electron pairs, that's always on the mark scheme, and therefore the bond angle gets smaller. So that's bond angle, and there's lots of practice questions to try at home and in class.